A silent spacecraft drifts through the darkness, powered by a revolution. This is the quiet revolution in next-generation propulsion. And it is not just about getting there faster. It is about transforming how we will live in the depths of space. For decades, the roar of chemical rockets defined space travel, limiting our ambitions with their violence and waste. But a new era of propulsion is changing everything, enabling deep space habitats that are sustainable, efficient, and designed for the long haul. By the end of this, you will understand exactly how these silent engines are building our future homes among the stars. We will uncover how something as seemingly simple as a gentle thrust can allow for larger windows in a habitat or even enable artificial gravity. What does a home that has never known the shudder of a rocket launch feel like? That violent shudder and deafening roar of a rocket launch is a testament to raw power, but it is also a cage. It defines a brutal, short-burst form of travel, completely unsuited for the vast, silent ocean between worlds. The quiet revolution begins by leaving that violence behind. Picture instead a vessel gliding through the void, its motion so serene it appears almost magical. This is the essence of the shift, a move from explosive chemical fury to the smooth, continuous push of next-generation propulsion. The goal is no longer just to escape Earth's gravity, but to thrive for years in deep space, where the constant shaking and noise of traditional engines would be unbearable and destructive. As Dr. Elena Rostova of the International Space Science Institute explains, the reduction in mechanical stress from these new systems is a game changer. It allows for more delicate scientific instruments that can make finer measurements, and it paves the way for genuinely habitable living quarters, not just cramped survival pods. So how do these silent engines work? The core principle is elegant. Instead of a brief, fiery explosion, they often use electric or nuclear power to accelerate tiny amounts of propellant to astonishingly high speeds. This creates a very gentle but incredibly persistent thrust that can run for months or even years. Think of it like the difference between a firecracker and a steady breeze. One is over in a flash, while the other can push a sailboat across an entire ocean. Two key technologies embody this. Ion thrusters use powerful electric fields to shoot out beams of charged atoms or ions. Plasma drives take this further, creating a superheated gas and using magnetic fields to hurl it away in a controlled jet. NASA's Dawn mission is a perfect example, using ion propulsion to journey to the asteroids Vesta and Ceres. Its gentle push accumulating over time to achieve speeds that would be impossible for a chemical rocket on the same amount of fuel. For the astronauts living inside a ship powered this way, the difference is profound. The constant, grating hum of machinery fades to near silence. The vibrations that slowly shake every bolt and wire loose are reduced to almost nothing. Your coffee does not ripple in the cup. Your sleep is not interrupted by a random shudder. This newfound stability is not merely a matter of comfort. It is the very foundation upon which we can begin to build true homes in the void. It allows us to rethink everything, from the fragility of the experiments we conduct to the very architecture of the habitats themselves. When your ship is no longer being violently shaken, what new possibilities suddenly open up for how we live and work in the deep dark? That first sputter of a liquid-fueled rocket in a Massachusetts field was a whisper compared to the thunder that would follow. For decades, the story of spaceflight was written in fire and fury, a necessary reliance on brute force to break the bonds of Earth. The mighty Saturn V rocket that carried astronauts to the moon was a masterpiece of power, but its immense vibrations shook every component to its core. a violent environment no human could endure for the years required to reach Mars or the outer planets. This was the fundamental limitation of chemical rocketry, a brilliant solution for escaping gravity but a terrible one for sailing the cosmic ocean. The fuel itself was the problem, a massive, heavy burden that left little room for anything else on a long journey. The quest for efficiency began to change the narrative. Unmanned probes like Voyager used the gravity of planets as a slingshot, a clever trick but one dependent on celestial alignments. Then came a quieter, more persistent alternative. The late 20th century saw electric propulsion prove its mettle not on flashy planetary missions, but in the steady, unglamorous work of keeping communication satellites in their precise orbits. A historian of aerospace, Dr. Kenji Tanaka, notes that this was the real turning point. It demonstrated that slow and steady could indeed win the race, that a gentle thrust maintained for years could achieve what a brief, powerful blast could not. This evolution from raw explosive power to refined, continuous control mirrors a broader pattern in our technology, from the clatter of early industrial machinery to the silent efficiency of a modern computer chip. The quiet revolution in propulsion was not a sudden breakthrough, but the inevitable next step for a species ready to build a home among the stars. So what are the specific engines that make this gentle, persistent thrust a reality? That faint blue glow is the silent signature of a spacecraft under power. Ion propulsion systems turn the void into a highway with a gentle, persistent push. They work by taking a noble gas, usually xenon, and stripping electrons from its atoms, creating a cloud of charged particles called ions. Powerful electric fields then accelerate these ions and shoot them out the back of the engine at breathtaking speeds. This is the core of its efficiency. While a chemical rocket throws a huge amount of propellant out quickly for a big push, an ion thruster throws a tiny amount of propellant out incredibly fast. It is the cosmic equivalent of a steady, light breeze that never stops blowing, gradually building up tremendous speed over time. This gives ion thrusters a specific impulse, a measure of fuel efficiency, up to 10 times greater than their chemical counterparts. For a deep space habitat, this efficiency translates directly into capability. Less mass dedicated to fuel means more mass available for life support, larger living quarters, and robust shielding against radiation. The mechanical benefit is just as profound. The violent shaking of chemical engines is replaced by an almost imperceptible vibration. This quiet operation is not just a luxury. It protects delicate scientific instruments from being jostled out of alignment, and it prevents the slow, structural fatigue that constant shaking inflicts on a spacecraft's frame. The European Space Agency's BP Colombo mission, currently on its way to Mercury, depends entirely on this smooth ride. Its suite of sensitive instruments would be useless after years of traditional rocket vibrations, but with ion thrusters, they will arrive in perfect working order. These systems are marvels of longevity, powered by vast solar panels that convert sunlight into the electricity needed to run them. With almost no moving parts, there is very little to wear out or break, allowing them to fire continuously for years. NASA's Deep Space One mission proved this was more than theory back in the 1990s, successfully testing an ion engine and validating the technology for the countless probes that have followed. But beyond the physics and the engineering, consider the human element. How might the quiet hum of an ion engine, a sound so subtle it blends into the background, affect a crew's mental state on a multi-year journey to another world? The constant, grating noise of machinery is a known stressor. Replacing it with near silence could be a vital ingredient for psychological well-being, making a metal hull feel less like a machine and more like a home. This stability is the first and most critical step in building a vessel that is not just a ship, but a sanctuary. While the blue glow of ion engines offers a gentle push, another technology delivers a more robust and decisive thrust. Deep within a shielded core, a nuclear reactor heats liquid hydrogen to temperatures that would vaporize steel. This superheated gas then screams through a nozzle, not with the explosive violence of a chemical rocket, but with a powerful, controlled roar. This is nuclear thermal propulsion, and it fundamentally changes the calculus of human travel to other worlds. Its key advantage is a perfect marriage of power and efficiency. It provides significantly more thrust than an ion engine, allowing for much faster transit times. A journey to Mars that might take 9 months with conventional engines could be slashed to just 4 or 5. This is not merely a matter of convenience. Every day spent in the deep space environment is a day of exposure to cosmic radiation and the debilitating effects of microgravity. Shortening the trip is a direct investment in crew health and safety. The thrust profile is also far steadier and more manageable than the violent, short-lived bursts of chemical stages. Experts from NASA, a Marshall Space Flight Center, emphasize that this steadiness minimizes the vibrational loads that can slowly shake a spacecraft apart, preserving the integrity of the habitat. For the people living inside, this means a smoother, quieter ride, free from the jarring shocks that could disrupt experiments or sleep. The benefits extend beyond the propulsion itself. The same nuclear reactor that heats the hydrogen for thrust can be tapped to generate immense electrical power for the entire habitat once the engine burn is complete. This one system could provide all the energy needed for life support, water recycling, food production, and lighting, creating a self-sufficient outpost. Safety, of course, is paramount. Modern designs use low-enriched uranium, which is far less weapons-grade material, and incorporate layers of shielding to protect the crew from radiation. The reactor would only be activated once the ship was already in a safe, high orbit, ensuring no radioactive material is ever present on the launch pad. The concept is not new. The NERVA program of the 1960s successfully ground-tested nuclear thermal rockets, proving the engineering was sound, though the political will to fly them faded. Reviving this technology brings its own ethical questions. How do we ensure public confidence in launching nuclear material into space? The answer lies in transparent engineering, rigorous safety protocols, and clear communication about the immense benefits for human exploration. Nuclear thermal propulsion offers a powerful yet controlled means of crossing the void, directly enabling the robust, long-duration habitats we will need. But what comes next when even the atom is not enough? A spacecraft can sail the void on light itself. Solar sails capture the faint but constant pressure of photons streaming from the sun, turning sunlight into motion. Picture a vessel with vast, silvery wings, kilometers across, made from a material thinner than a human hair. This is Mylar, a reflective film that billows out in the vacuum, catching the solar wind. There are no roaring engines, no vibrating machinery, and most importantly, no fuel to run out. The thrust is unimaginably gentle, a whisper of force that builds relentlessly over years. For a deep space habitat, this represents the ultimate in quiet operation. The constant minute acceleration is so smooth it is virtually undetectable, eliminating the disturbances that could ruin sensitive experiments or disrupt the peace of a long-term home. The success of the Planetary Society's Light Sail 2 mission proved this is not science fiction. That small craft successfully raised its orbit around Earth using only the pressure of sunlight on its sail, a historic demonstration of controlled solar sailing. For future habitats, such sails could act as perfect station-keeping engines, making tiny adjustments to their position without a single jolt from a conventional thruster. This passive propulsion system encourages us to think of the habitat not as a powered vehicle, but as a vessel integrated with its environment, harvesting momentum from the stars themselves. The challenges are immense, of course. Deploying a sail the size of a city block in microgravity is a feat of origami on a grand scale, requiring flawless engineering to prevent tearing or tangling. And for journeys beyond the inner solar system, where sunlight grows too faint to provide meaningful push, a more powerful light source is needed. This is where photonic propulsion enters the stage. Instead of relying on the sun, a powerful ground-based or orbital laser could beam concentrated light onto a sail, pushing it to speeds once thought impossible for human-made objects. The Breakthrough Starshot initiative envisions doing just that, using a giant laser array to accelerate a fleet of tiny, sail-equipped probes to a fraction of the speed of light, sending them to our nearest stellar neighbors within a human lifetime. This laser-sail hybrid hints at a future where our habitats are not just drifting, but are actively navigated across interstellar distances on beams of light. How might the passive nature of solar sails change our approach to designing habitats that are integrated with their propulsion? It suggests a shift from building complex, high-maintenance engines to crafting elegant structures that work in harmony with the fundamental forces of the cosmos. This is sustainability in its purest form, a silent, fuel-free journey that embodies the quiet revolution. With these gentle propulsion methods established, the stage is finally set to design the homes they will carry. That faint, continuous push from a next-generation engine does more than just move a ship. It fundamentally reshapes the home itself. Without the brutal shaking of a rocket launch, the entire philosophy of habitat design transforms. Engineers are no longer forced to build every component like a fortress, over-engineered to survive extreme vibrations. Instead, they can use lightweight, flexible materials that prioritize long-term comfort and efficiency. Imagine a habitat module with walls made of advanced fabrics or robust aerogels, materials that are excellent at insulating against temperature extremes and radiation, but would have been shaken to pieces during a traditional launch. Companies like Bigelow Aerospace have already demonstrated the potential of inflatable modules, which can be packed into a small rocket fairing and then expanded on orbit to create spacious living volumes. This is the new reality, where a habitat structure is designed for the serene environment of space, not the violence of leaving Earth. The internal layout is liberated as well. Without constant vibration, you can install large, panoramic windows that offer breathtaking views of the cosmos, something previously considered a structural weakness. You can design larger open spaces that reduce the feeling of claustrophobia during a multi-year mission. As space architect Dr. Maria Chen explains, quieter propulsion allows us to prioritize human-centric design. We can finally create environments that actively support mental health and productivity over years, not just basic survival for months. This shift enables more delicate and efficient internal systems. Advanced water recyclers that depend on precise membranes or precision agriculture units with fragile nutrient delivery systems can now function reliably for decades. The habitat itself can be modular, designed for easy expansion with new sections added over time, like building a neighborhood in orbit. Even critical systems like radiation shielding can be integrated more elegantly, with water or polyethylene layers doing double duty as part of the structural support. And perhaps most profoundly, the stable platform provided by gentle propulsion makes artificial gravity a more practical goal. A large, rotating habitat requires a perfectly balanced and steady rotation to avoid nauseating wobbles. a stability that was impossible with the shuddering engines of the past. The planned Gateway lunar outpost will be a testbed for this very philosophy, using advanced propulsion to maintain a stable orbit, which in turn allows for a habitat designed to test the systems and comforts needed for the journey to Mars. How might the aesthetics of these new space homes evolve when architects are freed from the constraints of the launch pad? We could see interiors that feel less like a submarine and more like a serene, modern home, with soft lighting, calming colors, and personalized spaces. This is not a minor improvement, it is a complete reimagining of life in space, all made possible by the quiet revolution in propulsion. The gentle hum of a next-generation engine is the sound of better sleep. An astronaut drifts through a full, restorative sleep cycle, completely undisturbed by the rumble of engines or the sudden jolt of a course correction. This is not a luxury, it is a fundamental pillar of health on a multi-year mission. The quiet operation of these propulsion systems directly combats two of the most pervasive stressors in space: noise and vibration. On a traditional spacecraft, the constant background roar is not just annoying, it can lead to genuine hearing damage over time. The subtle, incessant shaking works its way into your bones, disrupting sleep patterns, increasing anxiety, and making it difficult to concentrate. In a habitat powered by ion or nuclear thermal propulsion, that chaotic environment is replaced by a profound stability. The near silence allows for more accurate medical experiments where delicate cell cultures are not jostled by random vibrations. The life support systems themselves become more reliable as pumps and filters are not slowly shaken apart. We have evidence for this from analog missions here on Earth, in underwater habitats and isolated polar stations, where studies consistently show that a calm, quiet environment sharpens cognitive function and strengthens team cohesion. The design benefits cascade from there. Engineers no longer need to dedicate mass to extensive sound-dampening materials just to mask the roar of the engines. That saved weight can be used for something far more valuable, like enhanced radiation shielding or a larger greenhouse. The steady thrust profile also allows the crew to maintain a consistent day-night cycle, a critical element for circadian rhythms, without the schedule being shattered by noisy thruster firings. On the International Space Station, even small adjustments can ruin a sensitive experiment. With next-generation systems, those disruptive events are minimized or eliminated entirely. This new piece invites a revolutionary question. What kind of recreational or therapeutic spaces can we design when noise is no longer a limiting factor? Perhaps a quiet meditation room with a large viewport to the stars, or a small theater for enjoying films from Earth, experiences that would be impossible with the constant thunder of old technology. By prioritizing human well-being in this way, these quiet engines transform a long-term space mission from a grueling test of endurance into a genuinely livable experience. This focus on the human element is what makes true sustainability possible. A spacecraft that creates its own fuel is the ultimate deep space survivalist. This is the promise of closed-loop systems where propulsion and habitat are not separate machines but parts of a single, breathing organism. The quiet efficiency of next-generation engines makes this possible. Because they use so little propellant compared to chemical rockets, the waste products from the habitat itself can become a viable fuel source. Imagine water, the lifeblood of any crew, serving a dual purpose. After being used and recycled, a fraction of it can be electrolyzed, splitting it into hydrogen and oxygen. These gases can then be used in advanced propulsion systems, turning what was waste into thrust. This creates a powerful synergy where the very act of living and breathing on the vessel contributes to its journey. As Dr. Liam O'Donnell from the Space Sustainability Initiative points out, propulsion efficiency directly impacts the closed-loop systems required for multi-year missions, making sustainability achievable. This philosophy extends far beyond the ship's walls. The ultimate form of resource management is to live off the land. On the Moon or Mars, spacecraft could use local water ice, mined from permanently shadowed craters or the Martian soil to create propellant. This process, known as in situ resource utilization, transforms these worlds from mere destinations into cosmic gas stations. NASA's Artemis program is actively planning for this, with the goal of using lunar resources to support sustained operations. A lander that refuels using moon ice does not need to carry all its propellant from Earth, dramatically reducing launch costs and increasing its payload capacity for scientific equipment or habitat modules. The integration goes even deeper. The same nuclear reactor powering a thermal rocket can, after its burn is complete, provide all the electricity for the habitat's life support, food production, and water recycling for years. The massive solar arrays that feed an ion engine become the primary power source for the entire vessel. This eliminates the need for separate, heavy power systems, creating a lean and highly efficient architecture. Even the cleanliness of these propulsion methods contributes to sustainability. Unlike solid rocket boosters that litter orbit with debris, electric and nuclear systems leave no persistent fragments in their wake, helping to keep the space lanes clear for future travelers. So how could propulsion systems be designed to work in harmony with habitat recycling processes? The answer lies in seeing them as one integrated circuit. A water recycling unit is not just a life support machine, it is a propellant plant. A nuclear reactor is not just an engine, it is a power station for a farm. This seamless connection between how we move and how we live is the bedrock of a permanent presence in space. And managing such a complex, interdependent system requires a new kind of intelligence, one that can constantly balance the needs of the crew with the demands of the journey. That constant, gentle push from a next-generation engine creates a symphony of data, a flow of information so complex that only an artificial mind can conduct it. An advanced artificial intelligence system continuously analyzes the hum of the propulsion unit, the oxygen levels in the cabin, and the power draw from the greenhouse, making micro-adjustments to the thrust to keep the entire system in perfect harmony. This is not just automation, it is a deep integration where the engine and the habitat become a single, intelligent entity. For a crew traveling years from Earth, this artificial intelligence is their silent partner, a system that handles the immense complexity of their vessel so they can focus on exploration and survival. It autonomously navigates the void, plotting courses that instinctively swerve around dangerous radiation belts, all while balancing the energy budget between the engine's needs and the life support system's demands. Dr. Anya Sharma, an artificial intelligence researcher at SpaceX, emphasizes the predictive power of these systems. Machine learning algorithms can analyze sensor data to foresee a propulsion system failure weeks before a human engineer might notice the anomaly, preventing a catastrophic emergency in an environment where no rescue is possible. This predictive maintenance is a game changer for deep space habitats. The artificial intelligence does not just react, it anticipates. It can manage the crew's daily schedule, ensuring that delicate scientific experiments are not scheduled during a rare but necessary course correction burn. It integrates data from thousands of habitat monitoring sensors, linking environmental controls directly to propulsion. If a solar flare is detected, the system could automatically reorient the entire spacecraft to position its most heavily shielded section between the crew and the radiation, all while recalculating the flight path to compensate for the maneuver. We have already seen the seeds of this capability in the autonomous systems on NAS, a Perseverance rover on Mars, which makes certain navigation decisions on its own to avoid waiting for commands from Earth. For a crewed habitat, this level of self-sufficiency is not a luxury but a necessity. The light speed delay in communications means the crew must be able to trust their ship to handle crises instantly. How might this artificial intelligence-driven propulsion enhance the safety and autonomy of a mission to Jupiter's moons? It transforms the spacecraft from a mere vehicle into a resilient, thinking companion, capable of protecting its inhabitants from the unknown. This fusion of mind and machine represents the final piece of the quiet revolution, a leap toward habitats that are not just silent but truly intelligent. The economic ripple effects of this technological shift are just as profound as the engineering. The silent efficiency of these new engines is quietly rewriting the economics of space itself. That gentle, continuous thrust does more than push a ship. It pushes down the astronomical costs that have always limited our reach. For the first time, the business case for deep space is beginning to close. The fundamental shift lies in the dramatic reduction in launch mass. A next-generation propulsion system can require up to 90% less propellant than a chemical rocket to achieve the same change in velocity. This single fact cascades through every aspect of a mission's budget. Less propellant mass means a smaller, cheaper launch vehicle can be used, or that the same rocket can carry a much larger, more capable habitat. Suddenly, constructing a station in lunar orbit or at a Lagrange point shifts from a monumental, once-in-a-generation government project to something that private enterprises can realistically fund and pursue. Economic analysts project that the quiet revolution could slash overall mission costs by nearly 30% over the next 2 decades. This is not just about saving money, it is about fundamentally changing who can participate. The high cost of space has long been the single greatest barrier to entry, but as those costs fall, the gates begin to open. We are already seeing the early tremors of this shift. Companies like Rocket Lab are aggressively integrating electric propulsion into their small satellite platforms, proving that efficient, lower-cost operations are viable for the commercial sector. This paves the way for entirely new industries. Affordable, long-duration habitats could host pharmaceutical research in microgravity, manufacture unique materials, or serve as hubs for space tourism. The concept of in-orbit manufacturing, where asteroids are mined for rare metals, transforms from science fiction into a plausible business plan when the cost of transporting and operating the necessary machinery is no longer prohibitive. The reliability of these systems further fuels economic growth. With fewer moving parts and no explosive fuels, next-generation engines are inherently safer and more predictable. This increased reliability directly lowers insurance premiums, a significant line item for any commercial space venture. A new supply chain is emerging to support this economy, focused on producing and delivering advanced propellants like xenon gas. And perhaps most intriguingly, the very design of these propulsion units lends itself to reusability. Imagine a detachable, autonomous propulsion module that could be refueled at a space depot, then attached to a new habitat module, flying mission after mission. This reusability model, similar to the one that revolutionized rocketry with landing boosters, could be the final key to making deep space travel truly routine. How might this new economic accessibility reshape our vision of who gets to go? We could see universities funding their own research outposts, or nations with smaller space budgets collaborating on shared habitats. The quiet revolution is not just a technological leap, it is the foundation for a sustainable and inclusive future in space, built not on the fleeting fire of rockets, but on the steady, affordable push of a new dawn. The quiet hum of a shared engine could one day power a truly global village in deep space. International cooperation is no longer a lofty ideal, but a practical necessity for building the habitats of tomorrow. The immense cost and complexity of next-generation propulsion systems are simply too great for any single nation to bear alone. This reality is forging a new era of collaboration, where a habitat in orbit around Mars might be managed by a consortium of countries, its nuclear thermal engines built to common safety standards agreed upon in Geneva and Tokyo. The International Space Station stands as a powerful testament to what is possible, a complex machine assembled in orbit by nations that were once Cold War rivals. Its legacy is a blueprint for the future, one of standardized docking ports that allow modules from different countries to connect seamlessly, and shared resource pools where water and air are common assets. This level of integration requires a robust legal and policy framework. The foundational Outer Space Treaty, established in 1967, provides the initial principles, declaring space the province of all humankind. But the quiet revolution demands new, more specific agreements. How do we govern the use of nuclear propulsion, ensuring every nation is confident in its safety before a reactor is ever lit? How do we create equitable rules for extracting water ice from the moon to make propellant, so it does not become a source of conflict? Organizations like the United Nations Office for Outer Space Affairs are already facilitating these difficult conversations, working to establish the safety protocols and transparency measures that will build global trust. The potential for conflict over advanced propulsion is real, as the nation or corporation that masters these technologies first could wield tremendous economic and strategic power. The question is not just how we build these silent engines, but how we build the international institutions to manage them. How can we ensure the quiet revolution benefits all of humanity, preventing a new cosmic divide between the spacefaring and the earthbound? The answer lies in embedding cooperation into the very design of our future, creating shared habitats where propulsion is a bridge between nations, not a weapon. This global effort must now confront the final frontier of risk, the profound challenges that come with sailing into the absolute unknown. That faint blue glow of an ion engine is a lifeline, and its sudden silence could spell disaster. An engineer floats before a malfunctioning thruster millions of miles from home, with only the tools on board and the collective knowledge of the crew to find a fix. There are no resupply missions, no quick returns. This is the stark reality behind the quiet revolution's promise. For all their elegance, these next-generation systems carry profound risks that must be solved before we can truly call deep space home. The technical complexity is immense. A nuclear thermal rocket relies on materials that can withstand temperatures hotter than the surface of the sun, while ion thrusters demand flawless electrical systems that must operate for years without maintenance. Testing these engines on Earth is another major hurdle. We can simulate the vacuum of space, but we cannot truly replicate the years of cumulative exposure to deep space radiation and micrometeoroid impacts that will slowly degrade their components. This was a central challenge for the Variable Specific Impulse Magnetoplasma rocket, or VASIMR. This advanced plasma engine promised unprecedented control over its thrust, but its development faced repeated delays due to the immense difficulty of creating a power source compact enough for spaceflight yet robust enough to handle the engine's demand. The project highlighted a critical truth that bridging the gap between a brilliant laboratory concept and a flight-ready system is a marathon, not a sprint. For the habitats that depend on this propulsion, a single point of failure is unacceptable. A propulsion failure could leave a crew stranded in the void, unable to enter orbit around their destination or alter their course to avoid danger. This demands layers of redundancy, not just a backup thruster, but an entirely independent backup propulsion system, perhaps of a different type altogether. The ethical considerations are equally weighty, especially for nuclear systems. While modern designs are far safer, the public perception of launching radioactive material remains a significant barrier. A launch accident, however unlikely, could scatter debris and stall space exploration for decades. There is also a more subtle psychological risk. The quiet, smooth operation of these ships might breed a dangerous complacency. When the ride is as serene as a calm ocean, it becomes easy to forget you are sailing through the most hostile environment known to humanity. Crews could become less vigilant, their emergency response skills dulled by years of perfect operation. So what contingency plans are essential for surviving a propulsion failure in deep space? The answer lies in designing habitats for resilience, not just efficiency. Every system must have a manual override. Every crew member must be cross-trained in basic propulsion maintenance. And mission architects must always plot multiple trajectories, including free return paths that use planetary gravity to bring a crippled ship home without any engine power at all. Confronting these challenges is not a sign of weakness, but the final, necessary step in making the quiet revolution safe and reliable. This relentless drive to solve the unsolvable is already fueling a new wave of research, pushing the very boundaries of physics in search of the next great leap forward. A vial containing the most expensive substance in the universe is suspended in a magnetic trap. Inside, a few billionths of a gram of antimatter waits, each particle a key to energies far beyond our current reach. This is not science fiction, but the cutting edge of propulsion research, where the goal is to harness the total annihilation of matter and antimatter. The energy density is staggering, 1,000 times greater than nuclear fusion. For a deep space habitat, this could mean a propulsion system of unparalleled power and compactness, shrinking a journey to the outer planets from years to mere months. The challenge, of course, is monumental. Containing antimatter requires immensely powerful magnetic fields, as a single touch with any normal matter triggers a catastrophic release of energy. Yet projects like NASA's Innovative Advanced Concepts program are funding the foundational research to make this possible, exploring magnetic nozzles that could direct the resulting annihilation plasma into a controlled, unimaginably powerful thrust. This is just one of the radical ideas being sketched out in laboratories today. Fusion rockets, which would use small, contained star-like reactions to heat propellant, offer a more near-term leap, providing high thrust with fantastic efficiency. Even more speculative are theories that seek to bypass propulsion altogether. The concept of a warp drive, inspired by general relativity, suggests the possibility of contracting space-time in front of a vessel and expanding it behind, effectively moving the space around the ship rather than the ship itself. While firmly in the realm of theory, it forces us to ask a profound question. What does a habitat become when its propulsion is so advanced it is virtually imperceptible? A gentle warp in the fabric of reality that causes no vibration, no noise, and no acceleration forces. The design of such an interstellar arc would be completely liberated from the traditional constraints of an engine room, looking more like a floating city than a spacecraft. This future is being built on equally mind-bending physics. Superconductors cooled to near absolute zero could generate the massive magnetic fields needed for plasma propulsion without any energy loss. Some theorists even ponder the ultimate power source, the mysterious dark energy that is accelerating the expansion of the universe itself. The ethical dimensions of this research are as vast as the technologies. What are our responsibilities if we ever learn to manipulate the fundamental structure of spacetime? These questions were brought into sharp focus by the M-drive controversy, a concept for a propellantless thruster that appeared to violate the conservation of momentum. Though subsequent rigorous testing largely debunked it, the global debate it sparked was invaluable, demonstrating our collective hunger for a truly revolutionary leap. How might these futuristic propulsion methods transform our understanding of habitat design for interstellar travel? They suggest a future where the journey itself is so serene and stable that the habitat is designed entirely for life at the destination, a self-contained world that simply arrives, its passage through the void so smooth it feels as if it never moved at all. This relentless push into the unknown ensures the quiet revolution is only just beginning, and as our vessels grow more sophisticated, the lines between the systems that propel them and the systems that connect them to home begin to blur into a single, integrated network. That same gentle push guiding a ship between worlds also keeps its voice connected to Earth. A deep space habitat can use its ion thrusters to make tiny, almost imperceptible rotations, keeping a high-gain antenna perfectly aligned with a laser beam streaming from our planet. This is not a minor convenience, it is a lifeline. Next-generation propulsion provides the precise, low-power maneuvering that makes high-bandwidth communication possible across millions of miles. The steadiness of these engines ensures the laser link does not waver, enabling data transmission rates hundreds of times faster than traditional radio. For a crew facing a medical emergency, this could mean the difference between life and death, allowing a surgeon on Earth to guide a robotic procedure in near real time. It transforms the psychological experience of isolation too. Imagine a virtual reality call with your family, where the lag is so minimal it feels like you are in the same room, a powerful antidote to the loneliness of the void. This synergy is built on constant, fuel-efficient adjustments. Unlike clunky chemical thrusters that fire in jarring bursts, ion engines can nudge the spacecraft with the subtlety of a watchmaker, maintaining that perfect alignment for months on end with minimal power drain from the solar arrays. This precision also allows the habitat to proactively navigate the communication landscape. During a solar flare, which can scramble signals, the propulsion system can gently roll the entire structure, placing its bulk as a shield and then swiftly reorienting the antenna to a pre-arranged backup satellite node. This creates a resilient network where propulsion-enabled craft act as data relay stations, ensuring that a message from a Martian outpost always has a clear path home, even if the direct line is blocked. NASA Deep Space Network, our current ear to the cosmos, could be vastly augmented by such a web of smart, maneuverable nodes. How might this constant, high-fidelity connection reshape the social fabric of a deep space crew? The relentless isolation of a long mission could be softened by reliable, rich contact with home, reducing stress and strengthening the crew's mental resilience. This seamless link between how we move and how we communicate highlights a deeper truth, that every system in a habitat is intertwined. The same precise control that keeps the antenna pointed also guides the ship safely through the orbital highways of the solar system. That same precision which holds an antenna steady can also guide a habitat through a celestial ballet. Orbiting a distant asteroid, a vessel fires its ion thrusters in a series of faint, calculated pulses. Each burst is a whisper, a nudge so small it would be lost in the noise of an old chemical engine. Yet here, in the absolute silence, these tiny corrections are everything. They keep the habitat in a perfect, stable position relative to the asteroid's weak and irregular gravity, a feat of control previously unimaginable. This is the reality of deep space navigation, an environment where the comforting blanket of Earth's GPS is a distant memory. Without that constant signal, the ship must find its own way, relying on a suite of autonomous eyes. Star trackers take precise snapshots of the constellations, comparing them to an internal map to determine orientation. The propulsion system then translates those calculations into action, its gentle, continuous thrust providing the fine control needed to maintain orbit or execute a slow, precise approach. This symbiotic relationship between seeing and moving is what enables a habitat to park itself in the perfect spot for science, like hovering over a permanently shadowed crater to scan for water ice, or holding a stable position for optimal resource gathering. The proposed lunar gateway will demonstrate this principle on our doorstep, using its advanced propulsion to maintain a unique halo orbit around the Moon, a delicate balance point in the gravitational tug-of-war between Earth and the Moon. This is not a simple circle, it is a complex three-dimensional path that requires constant, subtle adjustments to maintain. Only a propulsion system capable of such gentle, persistent thrust could make this orbit a practical home. This precision becomes a matter of safety as we venture further. In the asteroid belt or around Mars, the risk of collision with natural debris or even other spacecraft requires a vessel that can maneuver gracefully, not lurch violently. The propulsion system acts as a vigilant guardian, its sensors integrated directly with the navigation computers. If a potential hazard is detected, the system can calculate and execute a safe avoidance maneuver long before a human pilot could react, using minimal propellant to shift the entire habitat's path. For the most ambitious journeys beyond our solar system, future navigation will look to the cosmos itself. Pulsar-based navigation systems are being developed, using the incredibly regular pulses from spinning neutron stars as a galactic lighthouse network. These pulses provide a timing signal so precise it could pinpoint a ship's location anywhere in the galaxy. But this only works if the ship can act on that information with equal precision. A low-thrust engine is the perfect partner, capable of making the tiny, continuous course corrections needed to follow a path defined by the steady beat of dead stars. What new challenges emerge when our habitats are no longer static bases, but mobile, navigating entities? The very concept of a space lane is born, requiring traffic management and coordinated maneuvers to avoid conflicts. Propulsion is the key to this new form of seamanship, transforming a drifting can into a nimble vessel capable of charting its own course through the gravitational currents and hidden obstacles of the void. This constant, intelligent maneuvering, however, demands a relentless and robust supply of power. A single reactor core could power both the gentle thrust pushing you toward Mars and the lights in your living quarters. This is the essence of integrated power and propulsion, a unified energy ecosystem where the lines between moving and living blur into a single, elegant system. The immense power demands of next-generation engines are not a burden but a catalyst. They force innovation in power generation that ends up benefiting every corner of the habitat. Whether it is vast solar arrays or a compact nuclear reactor, the primary power source does double duty. It provides the electricity for the ion thrusters or the heat for a nuclear thermal rocket, and then seamlessly transitions to running the life support, water recyclers, and food production units once the main engine burn is complete. This integration slashes mass and complexity. Instead of carrying separate power plants for propulsion and habitat functions, you have one. Designs for solar electric Mars transfer vehicles exemplify this, where the same massive solar wings that power the engines also charge the batteries for the crew's daily needs. This creates a leaner, more efficient architecture. To manage the ebb and flow of energy, engineers are looking at regenerative fuel cells. These advanced devices can store excess solar power by creating hydrogen and oxygen, which can then be recombined later to generate electricity for high power needs, like a sudden propulsion burst for an emergency maneuver. The biggest challenge in this unified system is heat. A nuclear reactor and its propulsion system generate immense waste heat that must be managed alongside the habitat's own thermal output. Sophisticated radiator systems, often integrated into the spacecraft structure itself, become vital, bleeding this excess energy into the void to prevent the entire vessel from overheating. Projects like NASA Kilopower are pioneering the small, safe nuclear reactors that could make this vision a reality, providing a steady 10-kilowatt output for a decade or more, enough to run a small outpost and its engines. This deep integration builds inherent resilience. If one part of the power system fails, the entire architecture is designed to reroute and compensate. How could integrated power and propulsion systems make habitats more resilient to failures? The answer lies in shared resources. A problem with the main reactor might force a shutdown of the primary engines, but the backup solar power could keep the life support online indefinitely, turning a propulsion failure from a death sentence into a survivable, if stalled, mission. This synergy is a cornerstone of efficient deep space living, a philosophy that extends to the very materials used in construction. That hull can now heal its own wounds. A habitat wall made of self-healing polymer quietly seals a microfracture caused by a tiny space debris impact, its internal chemical bonds reforming without any human intervention. This is the kind of material science miracle made possible by the serene environment of next-generation propulsion. Without the brutal shaking of a traditional launch, engineers are freed to use advanced materials that are lighter, stronger, and incredibly versatile, but would have been shattered by the violence of a rocket ascent. The palette of possibilities is vast. We can now design with metamaterials engineered structures that can bend and manipulate radiation, providing a far more effective shield against cosmic rays than a simple slab of metal. We can incorporate smart alloys that remember their shape, allowing a bent antenna or a damaged solar panel bracket to reform when heated. We can even develop biodegradable composites for temporary structures, breaking down safely after their purpose is served to reduce long-term orbital debris. This material revolution is deeply integrated with the habitat's functions. Imagine a hull that does not just block heat, but actively harvests it. The waste heat from the propulsion system, which would normally be radiated away, could be captured by thermoelectric materials embedded in the structure, converting it directly into electricity to power low-level systems. This turns a liability into an asset, making the entire vessel more energy efficient. For repairs, the concept of a supply chain from Earth vanishes. Instead, habitats will carry 3D printers that use local resources like lunar or Martian soil, known as regolith, to fabricate replacement parts on demand. The MIT Space Resources Workshop is a hotbed for this kind of innovation, developing processes to turn dust into durable, printed structures. The very skeleton of the habitat can become intelligent. By weaving microscopic sensors directly into composite materials, the hull itself can constantly monitor its own health, reporting stress, temperature, and even the location of an impact to the central computer long before a human eye would notice any damage. This level of self-awareness transforms the habitat from a passive shell into an active, responsive partner. But this incredible adaptability raises a profound ethical question. When we rely on novel, complex materials in an isolated environment millions of miles from help, what is our responsibility if they fail in an unexpected way? The crew's survival depends on the integrity of these advanced composites and polymers, materials whose long-term behavior in deep space is still being understood. This demands a new level of testing and a philosophy of built-in redundancy, ensuring that the very technologies created to protect us do not become a single point of catastrophic failure. This deep integration of smart, resilient materials is what will ultimately allow our habitats to be more than just shelters, but truly adaptable homes for the long journey. A habitat's propulsion system must be as resilient as the crew it carries. This means designing for failure, not just for success. Deep space offers no second chances, no rescue missions, and no quick returns to port. The solution lies in a philosophy of layered redundancy, creating a vessel that can lose critical systems and still bring its inhabitants home safely. Think of it not as a single engine, but as a network of independent propulsion pods. If one pod suffers a catastrophic failure, the others can automatically take over, recalculating the thrust distribution to maintain the ship's course and stability. This is not merely having a spare part, it is about having an entirely spare capability. The Orion spacecraft for the Artemis missions embodies this principle. Its propulsion system includes multiple redundant engines and thrusters, so even if several were to fail, the capsule could still perform the precise maneuvers needed to leave lunar orbit and slingshot back to Earth. This approach extends far beyond the engines themselves. Power sources are equally diversified. A habitat might rely on its main nuclear reactor for primary thrust, but have a bank of solar arrays and advanced fuel cells ready to power backup ion thrusters if needed. This ensures that a single point of failure in the power chain cannot cripple the entire propulsion system. Artificial intelligence is the silent guardian in this architecture. Machine learning algorithms constantly analyze performance data from every thruster, valve, and power conduit, searching for the subtle anomalies that precede a breakdown. They can detect a bearing wearing out or a fuel line beginning to clog long before a human engineer would notice, scheduling preventive maintenance or safely isolating the component. But what happens when multiple things go wrong at once? This is where the concept of graceful degradation becomes vital. The habitat is designed with fail-safe modes that prioritize the most critical functions. In a severe emergency, the system might automatically shut down all non-essential thrusters, conserve power for life support, and plot a new, simpler trajectory, perhaps a free return path that uses a planet's gravity to bring the ship home without any propulsion at all. The crews themselves are the final layer of redundancy. Astronauts on long-duration missions will be cross-trained not just as scientists or pilots, but as propulsion technicians. They will practice troubleshooting scenarios in simulators, learning how to manually bypass a faulty computer or perform physical repairs on a thruster feed line. This deep, practical knowledge transforms them from passengers into integral parts of the ship's survival system. How can we design habitats to remain safe and functional even after suffering multiple cascading failures? The answer lies in building interconnected yet independent systems, where the failure of one module does not doom the whole. This relentless focus on resilience does more than just prevent disaster. It builds the profound psychological confidence that allows a crew to venture into the absolute unknown, knowing their home is built to endure. That profound quiet allows for a different kind of sound, the easy laughter of a crew sharing a meal without raising their voices over a constant mechanical roar. This stability is more than an engineering metric, it is a social lubricant. In the confined, high-stakes environment of a deep space habitat, the reduction of noise and vibration directly nurtures healthier group dynamics. It minimizes the chronic low-grade stressors that, over months or years, can fray nerves and lead to conflict or isolation. We have a terrestrial blueprint for this in the isolated research stations of Antarctica, where studies consistently show that noise reduction leads to better mood, sharper cognitive function, and more effective cooperation. In space, where every interpersonal issue is magnified by the fact that you cannot leave, these benefits are not just pleasant, they are vital for survival. The design of the habitat itself can leverage this new quiet. Architects can create acoustically buffered private nooks for solitude and open, serene communal areas for socializing, all possible because the entire structure is not being constantly shaken. This propulsion-enabled stability also transforms the crew's connection to home. Imagine using a virtual reality headset to walk through a forest on Earth, an experience that would be jarring and nauseating with the random vibrations of old spacecraft systems. With next-generation propulsion, that virtual world remains perfectly stable, a powerful psychological respite from the metallic confines of the ship. Even the daily routine is sanctified by predictability. The crew can rely on a consistent day-night cycle, their sleep and work rhythms undisturbed by the sudden, noisy firings of attitude thrusters. On the International Space Station, such vibrations are a known disruptor capable of ruining delicate experiments. For a human crew, that same disruption ruins peace of mind. So how might this unprecedented quiet influence the very culture of an off-Earth community? It could foster the development of more contemplative, cooperative societies, where the absence of environmental stress allows for a focus on art, science, and community, rather than mere survival. This deep understanding of human psychology is not a secondary concern, but a core requirement for missions that will last for years. Ensuring these future explorers are prepared and that the public back on Earth remains engaged and supportive becomes the next critical frontier. A live stream from a deep space habitat shows a high school physics class the serene blue glow of an ion engine, its silent operation a stark contrast to the fiery rockets of old cinema. This is the quiet revolution's front door, an invitation to see space not as a hostile frontier, but as a place of elegant, accessible technology. Educational outreach transforms these complex systems into relatable stories. Students can now run simulations on classroom tablets, guiding a virtual habitat with gentle thruster pulses, learning the principles of orbital mechanics through direct, hands-on play. Museums are building interactive exhibits where you can feel the subtle difference between the vibration of a chemical engine and the near-silent hum of a plasma drive, making the engineering tangible. Social media campaigns shift the focus from the machinery to the people, showcasing an astronaut's typical day in a habitat so stable her coffee doesn't ripple, highlighting the human comfort this technology enables. These efforts are being woven into new curricula that connect propulsion directly to sustainability goals on Earth, framing the closed-loop systems of a spaceship as a masterclass in resource management. Citizen science projects invite the public to analyze real habitat data, looking for patterns in radiation shielding effectiveness or the performance of water recyclers, turning everyday people into active participants in the mission. NASA CubeSat launch initiative is a powerful example, giving university students the chance to design and fly their own small satellites, often equipped with miniature versions of these very propulsion systems. The stability provided by gentle thrust even enables virtual tours, where a 360-degree camera inside the habitat can provide a rock-steady, immersive view for anyone with a VR headset, eliminating the disorienting shake that would have plagued such a tour in the past. How can we leverage these serene and sophisticated advancements to tear down the old barriers to space science, making it feel more inclusive and engaging for communities that have historically been left out of the conversation? This broad public engagement is not a side effect of the quiet revolution, it is its lifeblood. Widespread understanding and excitement are what build the political will and secure the long-term funding required for such ambitious projects. Making the science accessible ensures that the future of deep space habitation is shaped by a chorus of many voices, not just a select few. This foundational work of education and outreach naturally leads us to confront the larger ethical responsibilities that come with building a permanent presence beyond our world. That debate in a secure conference room centers on a single, profound question: who gets to decide the acceptable risks of a nuclear thermal engine firing near the orbit of Mars? The quiet revolution is not just an engineering challenge, it is a global ethical dilemma, forcing us to write new rules for the road before we have even built the car. The core of the issue is the precautionary principle, the idea that we should avoid actions that could cause severe or irreversible harm, even if the scientific evidence is not yet complete. Applying this to propulsion means asking whether we have the right to risk contaminating a potentially life-bearing world like Europa with a nuclear-powered craft, or to alter the delicate orbital environment around another planet with our exhaust plumes. The Moon Agreement of 1979 touched on these ideas, suggesting that celestial bodies should not be disrupted by harmful contamination. But our new propulsion technologies add urgent, complex layers. For the crews who will rely on these systems, the ethical concerns are deeply personal. Informed consent becomes a matter of life and death. An astronaut signing up for a mission using an experimental plasma drive must fully understand not just the immediate risks of launch, but the long-term statistical probabilities of a system failure millions of miles from help, and the potential health effects of years spent living next to a nuclear reactor. This is not like testing a new car on a closed track. It is a one-way journey into the absolute unknown. Governance struggles to keep pace. Current space law, rooted in the Outer Space Treaty, makes nations liable for damage caused by their space objects. But what happens if a malfunctioning private habitat using advanced ion thrusters accidentally collides with a scientific outpost? The legal and financial responsibility could be astronomical, stifling innovation or creating victims with no clear path to justice. The problem of space debris is also intensified. While electric propulsion itself is clean, the increased traffic it enables raises the risk of collisions that could generate new clouds of orbital shrapnel, jeopardizing all future travel. We must confront the potential for these technologies to create a new divide. If one nation or corporation masters efficient propulsion and claims the best orbital slots or resource-rich asteroids, it could create a cosmic inequality, leaving other actors behind. How do we ensure that the ability to move efficiently through space does not become a tool for exclusion? The answer lies in building ethical frameworks into the design process itself, not as an afterthought. This means international panels setting clear safety standards for new engines, transparent protocols for accident response, and global agreements on the equitable use of propellant mined from the Moon. Deciding the limits of this power is perhaps the most difficult test of the quiet revolution, a test that will determine whether our future in space is one of cooperation or conflict. This ethical groundwork is what will finally clear the path for the ultimate journey, pushing beyond the familiar planets toward the beckoning light of other stars. A generation ship coasts through the interstellar void, its journey measured in lifetimes rather than years. This is the ultimate destination of the quiet revolution, where propulsion systems become so seamlessly efficient they fade into the background of daily life. To reach another star within a human time frame, we need to leap beyond even our most advanced nuclear engines. Concepts like fusion rockets, which harness the power of miniature stars, or the staggering energy density of antimatter drives, promise to compress travel times from millennia to mere decades. These are not engines of brute force, but of profound, sustained power. For the habitat, this reality demands total self-sufficiency. the vessel is no longer a ship, but a traveling world where propulsion is woven into the very fabric of its existence. The same fusion reactor that pushes it forward also powers the artificial suns in its agricultural modules and the vast recycling systems that cleanse every drop of water. The challenge of sustaining a closed ecosystem over centuries is monumental. Every element must be perfectly balanced, a delicate dance of oxygen, carbon, and nutrients that cannot afford a single misstep. This forces a psychological evolution for the crew. For a multi-generational mission, the concept of Earth shifts from a home to a mythic origin point. The ship itself is their entire universe, and its gentle, continuous acceleration is the one constant across generations. To manage this, scientists are exploring hibernation technologies, where crew members sleep through the long dark, their metabolic rates slowed to a crawl while the ship's autonomous systems and steady propulsion carry them onward. The Breakthrough Starshot initiative provides a glimpse of this future in miniature, aiming to accelerate a fleet of tiny probes to a fraction of light speed using giant Earth-based lasers. While these are just probes, the principle is the same, using a persistent external propulsion source to enable an interstellar journey. This raises a profound social question. What unique culture might develop on a vessel where the engine's hum is as natural and unnoticed as the sound of blood in your ears? The crew's entire existence, their art, their language, and their beliefs would be shaped by the reality of a journey they did not choose, propelled by a force they may not even fully understand. These interstellar ambitions represent the final frontier for the quiet revolution, pushing its principles to the absolute limit and forcing us to reconsider the very meaning of economy when the journey spans light years. These silent engines are building the framework for a bustling space economy. Picture a future where private companies operate entire fleets of vessels, their quiet propulsion systems humming as they ferry tourists to orbital hotels and deliver critical cargo to research outposts. This is not a distant dream, but the direct result of the propulsion revolution making space travel affordable and routine. The quiet efficiency of these engines dramatically lowers the cost per mission, transforming activities like asteroid mining and space manufacturing from speculative ventures into plausible business plans. For the habitats themselves, this commercial boom means everything. Instead of relying solely on government agencies, a deep space habitat could partner with private entities for regular resupply, module expansion, and even specialized maintenance, fostering a market-driven ecosystem far from Earth. This gives rise to new business models like propulsion as a service, where a company might not sell you a spaceship, but rather a guaranteed amount of thrust, managing the complex engines for you as a utility. This burgeoning industry creates entirely new job sectors, from in-space propulsion technicians to orbital traffic controllers, building a workforce that lives and works off the planet. The technological spillover is equally significant. The advanced propulsion systems developed for these quiet ships could revolutionize travel on Earth. SpaceX's vision for its Starship vehicle to enable point-to-point travel across our planet in minutes is a prime example, using the same fundamental principles of efficient, powerful rocketry to shrink our world. This vast economic potential attracts immense investment, fueling a virtuous cycle of innovation that makes the entire architecture more capable and less expensive with each passing year. Yet this commercial gold rush raises crucial questions. How might the drive for profit influence the safety standards of a habitat millions of miles from help? Could competition lead to a clutter of incompatible systems, or will market forces eventually create the universal docking ports and safety protocols that ensure everyone can work together? The promise of accessibility is profound. potentially allowing universities and smaller nations to establish their own footholds in space. But it must be balanced with a steadfast commitment to making deep space a safe and sustainable environment for all. These silent advancements form a single, unified architecture for living in the void. The gentle hum of an ion engine, the predictive gaze of artificial intelligence, and the resilient materials of a self-healing hull are not isolated breakthroughs. They are threads woven into a single fabric, each one strengthening the other to create a habitat that is far more than the sum of its parts. This holistic shift redefines our entire approach. We are no longer just building ships to survive the journey, but crafting homes that enable us to thrive for generations. The propulsion system's stability allows for delicate life support recyclers. The artificial intelligence that manages the engines also safeguards the crew's health. The international cooperation that funds the venture ensures its long-term sustainability. Key principles emerge from this synthesis, lessons that will guide our future. Redundancy is not a luxury, but a fundamental design philosophy, creating vessels that can endure multiple failures and still bring their crews home. Collaboration is the practical engine of progress, uniting global resources and knowledge to overcome challenges no single nation could face alone. And underpinning it all is a profound ethical imperative, a responsibility to move thoughtfully into this new realm. We must ask ourselves a crucial question as we stand on this threshold. How can we ensure that the power to build these silent, efficient homes among the stars is used to uplift all of humanity, and not just a select few? The answer will determine whether our cosmic future is one of isolated outposts or a connected, interstellar community. This collective vision prepares us for the final and most personal consideration of all. This quiet hum is the sound of a fundamental shift in human destiny. We have moved beyond the age of simply surviving the journey to the era of designing a life worth living in the void. The technologies we have explored, from the steady blue glow of ion engines to the controlled power of nuclear thermal rockets, are far more than engineering marvels. They are the essential foundation for a new chapter in our history, one where deep space habitats transform from cramped, temporary outposts into sustainable, enduring homes. This is the true promise of the quiet revolution. By eliminating the destructive noise and vibration of past systems, we unlock the potential for habitats that actively support human health, that allow for structural innovations with lightweight materials and expansive windows, and that operate with a resource efficiency that borders on the magical. The implications ripple outward, from slashing the travel time to Mars to making the dream of interstellar travel a tangible goal for future generations. This journey fosters unprecedented international cooperation and seeds the growth of a new off-world economy. The visionary Carl Sagan once reflected that somewhere, something incredible is waiting to be known. The quiet revolution is our vehicle to those unknowns. It is the key that will unlock not just new worlds, but new ways of being. I would love to hear your thoughts on these incredible advancements in the comments below. And if you want to continue this futuristic journey with us, be sure to subscribe for more insights. Remember, we are not just watching this history unfold. Together, we are helping to build it.